Hey, this is just a video on radicals and rational expressions from the topic A3 in grade 11 math. Okay, so let's just talk radicals really quickly. So here's how we can simplify radical expressions. So if we have the square root of 50, we want to put the radical into lowest terms, kind of like into its most simplified form. So what we're going to do is we're going to look for perfect squares inside of that radical. So perfect squares are things that you can square root and get a whole number. So like 1, 4, 9, 16, 25. We get these numbers by doing 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, etc. So we know all these numbers will have a whole number that when you square root them. So when I look at the number 50, I try to think, well, what are two things that multiply to 50? 5 and 10, 25 and 2. And I'm trying to look for numbers that appear here. So I can see that 25 is a perfect square. So I'm going to simplify root 50 into 25 times 2. Now I can break up this root into two roots. So I can break it up into root 25 times the square root of 2. And that will still equal the square root of 50. And now what I can do is, I know that the square root of 25 is 5. So I can actually calculate that. So that's 5 times the square root of 2. And then I can just write it without that multiplication sign. So 5 root 2 is the same thing as saying 5 times root 2. So that would be a radical in simplest terms. So we want to pull out any perfect squares that exist under the radical sign. We call this guy the radicand. So if there's any perfect squares in there, we want to pull them out of the radical sign and then simplify them. So 5 root 2 would be the answer. Okay, and then here's how we add radicals. So it turns out we can only add them if they have the same radicand. So these guys both have a radicand of 2. So then we can just do 3 plus 4 is 7 root 2. It's almost like adding like terms, like 3x plus 4x is 7x. So we can do that. If they don't have the same radicands, then we can't do anything. Here's an example of just multiplying a couple binomials that have radicals. So I'll show you a long way and then I'll show you a shortcut. So we're doing what we normally do. We're multiplying everything in the first bracket by everything in the second bracket. So what's root 2 times root 2? It would be the square root of 4. What's root 2 times negative 3 root 5? It would be negative 3 root 10. Then we move on to this one. We multiply it by everything in the second bracket. So 3 root 5 times root 2 would be positive 3 root 10. And finally, these guys are multiplying together. So we do negative 3 times 3 would be 9, and root 5 times root 5 would be root 25. Sorry, that's almost didn't fit that. And then we'll just simplify it all. So we know the square root of 4 is just 2. We know negative 3 root 10 and positive 3 root 10 are going to just cancel right out. So that's going to be 0. And then 9 root 25 can simplify to 9 times 5, because the square root of 25 is 5. So it would be 2 minus 9 times 5 is 45. And then 2 minus 45 is negative 43. Okay, so a quick way to get to this answer is, we notice that it's actually kind of like a difference of squares, like x plus 3, x minus 3, which simplifies to x squared minus 9, or x squared minus 3 squared. So if you know that pattern, you can actually do this really quickly by following this pattern. So your first term is a root 2. So it's going to end up being like root 2 squared minus your last term is 3 root 5 squared. So your final answer, so root 2 squared is going to be just 2, because the square root and the 2 cancel out. And then 3 root 5 squared is going to be 9 times 5, because this guy is cancel out, but we're still squaring the 3. So 9 times 5, so 45, so negative 43. So you could expand that one pretty quickly if you know the difference of squares algorithm. Okay, so that's radicals. That's what we learned about radicals. Next is rational expressions. So let's just warm up with a couple of simplifying questions. So say you had a fraction like 6/8, and we wanted to reduce it to lowest terms. We can think like, oh, we would divide both of those by 2. Or another way to think about it is, 6 is a product of 2 and 3, so 2 times 3 is 6, and 8 is 2 times 4, and we're kind of canceling out those 2's to end up with 3/4. Or whatever, we're dividing the top and the bottom by 2 to end up with 3/4. So this is simplifying or reducing. I'm going to call it simplifying. So we always want things simplified to lowest terms in math. And that's just because it's easier to compare things that way. If everything's always simplified, we know if something's the same or different. So we always want things in lowest terms. So we're going to simplify stuff that contains x's and a whole bunch of crazy expressions. And it's basically by dividing it by a common factor. That's what we're doing. I just want to warn you though, like I see this happen a lot where you see an expression like 3 plus 7 and then it's divided by 3. And a lot of people will try to do this, like cancel out the 3's. Okay, we can't do that. Because really what this is like a fraction like 3/3 plus 7/3. So sure, these could cancel, but we'd end up with 7/3. We wouldn't end up with just a 7. So you just have to be careful. Like when you're canceling, you're not just crossing stuff out. What you're really doing is you're dividing each term in the bracket by 3. So just a heads up on that. Okay, so let's talk variables. So if we want to simplify 10x squared divided by 8x, we're just going to look for common factors. So I see that they're both divisible by 2 and an x. So I'm going to divide the top and the bottom by 2x. And I'll end up with 10 divided by 2 would be 5. And x squared divided by x would just be x. And on the bottom, 8 divided by 2 will be 4, and x divided by x would just be 1. So that would be my expression in simplest forms. So this would be the answer. So all I did was divide the top and the bottom by 2x. Okay, now there's something weird that we have to do with these. After we simplified them, we have to do something called stating restrictions. Because we've altered the original equation, so this was the original equation or expression. Because we've altered it, we've got some like restrictions. We've got some limitations for x. There's something x can never be. So if you were to sub values in for x, you can never sub 0 in for x. And why is that? Because if you did, at one time there was an x in the denominator. So if you subbed a 0 in for x, your expression down here would equal 0. And we never want 0 to be in the denominator. So even though this guy doesn't have an x in the denominator, it once did. So we have to do this thing every time we simplify expressions with variables. We have to state restrictions. And to state the restrictions, we just set the denominator equal to 0 and then solve for x. And then that becomes our restriction. And let me just give you a visual. So ignore my top equation here, but in the bottom one, if I were to graph 10x squared divided by 8x, I would end up with a straight line. I would actually end up with this, 5x over 4. So a slope of 5 over 4 and a y-intercept of 0. That's what I've got here. But there's something interesting. So if you were to like narrow in on 0, I'm going to try to. Check out the point. 0 is actually undefined for the y value. So if x is 0, there's no y value there. So what we have, Desmos doesn't really show it, but it does show it when you try to click on it. We have a hole in our graph at 0. So this equation, 10x squared divided by 8x, produces a straight line with a hole at 0. Oops. Just started guided access. Sorry about that. So we have to do this restriction stating thing every time. Okay, so let's take this guy. 3x plus 9 divided by x plus 3. We want to try to simplify it. Okay, so it's not really obvious what we can cancel out. So here's a tip. Sometimes we're going to have to factor first before we can simplify. So you're always going to have to do this. So you're going to look at the top and you're going to be like, is there anything I can factor? Is it a trinomial? Is it a difference of squares? No, but it does look like they both are factorable by, there's a common factor of 3. So I'm going to common factor out a 3 from my numerator, leaving x plus 3. And the bottom's going to stay the same. So now I can see that I actually do have, they're both divisible by x plus 3. So I can divide the top and the bottom by x plus 3, leaving me with just a 3. And then I would have to state any restrictions. So remember, I get my restrictions by setting the denominator of the original expression equal to 0. So x plus 3 equals 0. I'm going to say doesn't equal 0 because I don't want it to. And then I'm going to pop the negative 3 on, or I'm going to pop the 3 on the other side, or subtract 3 from both sides, making my restriction x cannot equal negative 3. So if I were to like graph this equation, which you're going to in grade 12 math, I would know that it's going to have a hole in it at negative 3. So once I reduce this, I'm going to have a graph at y equals 3. So I'm going to have this graph that looks like this. But when x is negative 3, there's going to actually be a hole in my graph. Okay, next question. X squared plus 10x, x squared plus 7x plus 10 divided by x plus 5. Okay, so to simplify this expression, we should factor first. So if we look at the top, it's a trinomial. So what multiplies to 10 and adds to 7? X plus 5 times x plus 2 divided by x plus 5. So now I can see that I have a common factor. I have like something I can factor out. Something that's common in the top and the bottom is x plus 5. So I'm going to end up with just x plus 2. And my restrictions. So if I look at my original denominator, I've got x plus 5. I don't want that to equal 0. So it looks like x cannot equal negative 5. Okay, and let's try a slightly trickier one. So let's say we had x squared plus 10x plus 21 divided by x plus 3. And then I'm going to multiply that with another fraction, x plus 2 times x squared plus 9x plus 14. Okay, I want to simplify this. So what do I do? Factor first. Factor everything I possibly can. All right, so my top is a simple trinomial, what multiplies to 21 and adds to 10. So 7 and 3. So x plus 7 and x plus 3. Leave my denominator. And multiplied by, I've got an x plus 2. And in my denominator, I've got a simple trinomial again. So what multiplies to 14 and adds to 9. So x plus 7 and x plus 2. So now I'm going to just go around and cancel everything. And remember when you're multiplying, like I could actually put these all in one fraction together. I could write this like, sorry, my pen's being weird. X plus 7 times x plus 3 times x plus 2. And then the whole thing is divided by x plus 3 times x plus 7 times x plus 2. Because multiplying fractions, you just multiply the tops and multiply the bottoms. So I could just multiply that all together. And then I can just cancel out my common factors. So I got x plus 7s, x plus 2s, everything cancels. So I'm actually just left with 1. So my final answer would be 1. But I'll have a whole bunch of restrictions. So for my restrictions, I'm going to look at my factored version here. So I don't want x plus 3 to equal 0, which would result in x can't equal negative 3. So that's one of my restrictions. I also don't want x plus 7 to equal 0, which would result in x can't equal negative 7. And finally, I don't want x plus 2 to equal 0, which would result in x can't equal negative 2. So I have 3 restrictions this time. And I ended up with just a 1. So that's how you simplify rational expressions. Now the factoring could get harder. I did pretty easy factoring. I just did like simple trinomials. But you might have some complex trinomials, some difference of squares. So your goal in this expectation is factor every single thing you can. Factor, whatever you need to, factor it. And then look for things that are the same on the top and bottom and try to cancel them. And then state your restrictions. And that's it.